Today's lesson is sourced from Chapter 1 of Mechanics of Materials. It'll be broken up into two parts. First, we'll review some key concepts, and then we'll solve an example. We'll start by bridging the gap in our understanding of stress. Almost all of us have experienced stress as a result of demands in our lives, but let's examine stress as we know it in the engineering world. Stress is defined as the internal force in a material that counteracts the external force acting on a cross-sectional area. Now, that's a pretty lofty definition, but it's essentially a force per unit area. So the units of stress are usually written as pounds per inch squared or newtons per meter squared, which is also called a Pascal. Since there are two types of internal forces, there are also two types of stresses. The first is normal stress, which results from a force that's applied perpendicular to the cross-section. The average normal stress can be written as sigma equals N over A, where sigma is the average normal stress, N is the internal resultant normal force, and A is the cross-sectional area. But before we solve any problems, let's figure out what the cross-section looks like on an axially loaded bar. To be axially loaded means that the bar has forces, or loads, running through its axis. We'll make an imaginary cut across this bar perpendicular to its longitudinal axis. This area is called the cross-section. So if the bar is axially loaded, that means the normal force either acts as if it's pulling on the area, like this, or pushing on the area, like this. If it's pulling, we say that the bar is in tension, kind of like when you pull two sides of a rubber band. If it's pushing, we say that it's in compression, which is more like when you crush a soda can. The second type of stress is called shear stress, which results from a force that's applied parallel to the cross-sectional plane. The average shear stress can be written as tau equals V over A, where tau is the average shear stress, V is the internal resultant shear force, and A is again the cross-sectional area. Our last key concept involves allowable stress design. This basically boils down to the idea that although a structure can support a large load, we probably shouldn't push it to its limits. Otherwise, we may end up with this. We use a value called the factor of safety to determine the amount of force a structure can handle. The factor of safety for specific materials can be found in engineering handbooks and design codes. The formula for the factor of safety is failure load over allowable load. We can also write it as failure normal or shear stress over allowable normal or shear stress. We can do that because if we rearrange the average normal and shear stress formulas, we get force equals stress times area. Over here, I used the example of only normal stress, so we'll go ahead and just use sigma and the normal force. Since the areas cancel out, we can replace the failure and allowable loads with their corresponding stresses.